Hi guys, welcome back to Data Every Day. Today we're looking at a data set of avocados, which is basically just lots of avocados. We got all these different features about different avocados, and we're going to try to be predicting if it is conventional or organic. So let's go ahead and start up a notebook, and we can load in our data over here. I'll just quickly import our standard libraries. Just these two to start. Just want to get a quick look at the data. So data equals pandas.read CSV. And this I'm going to paste in the file path here. Take a look at it. And we have 14 columns. So 14 features. Actually 12 features, because we're going to take off this first one. And then we're going to use type as our label column, right? So let's go ahead and just drop that first one, because we definitely don't need that. It's just an extra ID column. And so let's see. Wait, what is this? This isn't actually an ID column? What? It's weird. This is example 18,000, and there's a number 11 here. See if it says something about it here. It says index, but it resets. What's it resetting by? Does it reset by month? It's too hard to say. Let's just get rid of it, okay? We have a better index on the side, and we're not going to need this. So I'm just going to say data.columns sub 0. We get the first one. Axis equals 1, in place true. And then we should be able to, should be gone. And then we're just going to get some preliminary information about the data set. Alright, and it looks like we have, looks like no nulls, right? This is 18,249 examples, and every one is non-null for every column. Additionally, we only have 1, 2, 3 string columns, or text columns, one of which is the one we're predicting. So minimal encoding and pre-processing on this data set. Let's start getting into it, though. What we do have to do. First, let's just take, you know what, why not before we pre-process, let's take a look at some of the data. Let's try to check if we have any like ridiculous outliers. So I'm gonna import, we'll use pyplot, and then we're just gonna set up a new figure. We'll say 20 by 10, should be good. And then I'm going to make, box plots, which will show us if we have any outliers we have to take care of. And like small outliers that are close to the mean relatively are going to be okay, but ones that are like really far out, we want to take a look at that because it might be a numerical error. So for I in range, length of data.columns, so basically for each column, if data.dtypes sub I, so if the ith dtype, the dtype for the ith column, is not an object, so this is basically saying if we're dealing with a numerical column, then we're going to create a new subplot in a 3 by 5 grid indexed by I plus 1, and we're going to plot in that subplot a box plot of the ith column. And this is the column name, so I'm just indexing data at the column name. And let's do vertical equals false so we can get horizontal box plots. And we'll give it a title, which will just be the ith column name. Alright, when it's done, plot.show. Let's see. Oh, what's wrong? Oh, it should be columns. Here. Alright, and we can see, this is just a quick way to see if our data has any outliers. And I mean, these ones over here, you can see all the values are concentrated at near 0, right? And this you could say is an outlier, but it's not that bad, right? Like, there's nothing here that's like blatantly outlier. So you can see, even though it's concentrated at 0, it's still a good amount of spread out towards the edge, towards higher values for all of these. So I don't think we have to worry in this case. This looks pretty good. So the data set's looking pretty have good prospects for this one. So let's take a look at the null values. I'm pretty sure there's none, as we saw before. But just to double check, there's 0 in every column, so we don't have to worry about it. Alright, so let's start encoding. What I'd like to do to begin encoding is get a function called getUniques, which will take in some data frame and a list of columns that we want to get the unique values for. And this is, we really want to get the unique values for all the categorical features, right? So we're going to return a dictionary that maps a column name to a list of the unique values for that column. So each column is going to be mapped to a list of its unique values. And that's for every column in columns that we specify. Okay? Then we're going to create a list of categorical features, which is just going to be, where is it? Date is one. Type is not a feature, but we could include it just to get some idea. And region. So date, region, and we'll do type. Since type isn't actually a feature, we'll just say categorical columns. And so it's region, date, and type. Whoops. Alright, and then we're going to get the unique values on our dataset with the column specified above. And now we can see region's unique values are, as expected, they're names of cities and areas. And date is also to be expected, just dates. And it's a good thing that it's in year, month, day format so that we can sort it very easily. And the type is just a binary, which we'll be predicting conventional or organic. So what I usually like to do is split them into variables, just so I can keep track of like what kind we're dealing with. The date is going to be an ordinal feature, so we'll put date in there, and the region is going to be a nominal feature. And then we'll just say our target column will be type. Okay, so we encode these two differently, right? Target column we'll use, let's use a label encoder. So before we move on, I'm just going to import label encoder and a few other processing tools. Import label encoder, and I realized I forgot sklearn. sklearn.preprocessing. And then let's just import from the same library standard scalar. And the reason I'm using standard scalar here, not min-max scalar, is because standard scalar is a little more robust to outliers. And as you can see, like these guys, in a min-max scalar, this would become the max, and there'd be all this wasted space before any of the real data started coming in. So a standard scalar will take this less into account. Alright, so then we're also going to import, oh wait, this should be from, sorry. And then from sklearn.model_selection import train test split. And then we'll use TensorFlow for this one. Okay? So we'll start by creating two functions. One will be Ordinal Encode. Takes in some data frame, a column, to encode, and an ordering for that column. And the other one will be one-hot encode, which will be for our nominal features. Takes in a data frame and a column to encode. Alright, so for ordinal encode, this is going to be a simple function. First, let's just create a copy of our data frame so that we're not accidentally modifying in place. Sorry, df.copy. And then we can, we're going to create basically a lambda function that's going to map each value in the dates, right, because that's what we're ordinal encoding here, to a number that corresponds to its order in ordering. So if that's confusing, let me just show you. Data subdate dot unique. This is a list of all the unique dates, and if we just sort that list, we'll get it in basically chronological order, right? This is because January 2015 will be at the very top, and it will go through year by year, going through the months up until 2018 of March. So this is going to be our ordering. Luckily, the format was already in that format, so that we are able to sort it just using the sorted function built in from Python. So date ordering is going to be this guy. And notice that if we index date ordering dot index some date, if we take some date, right? Just take this guy. If we index at this place, we get the list, the location in the list. So more recent dates are going to have higher values, and older dates are going to have lower values. So this is a convenient way of basically, it won't be so much a date column anymore, but it will be like a time column. So the model will be able to distinguish between avocados from long ago and avocados from the more recent times. So with this, we're going to say, okay, df subcolumn, we're going to map a lambda function to it with pandas apply function, apply method. Going to map this lambda function that takes in some x and returns the ordering.index of that x. So it's like what we're doing here, right? X is going to be some date, and it's going to change each date into its index in the ordering that we specify. And then when that's done, we'll just return df. Okay? Now for one hot, we're going to, well, first let's make another copy, just in case. And then we're going to create a dummies data frame. So pd.getDummies will take in some column or some split of a data frame. So let's use region, which is the one we're going to actually use. And this will take every unique value in region and give us a matrix of ones and zeros, where a 1 corresponds to the presence of that value in that example. So 0, 1, all the way through 4 is Albany. And you can see at the very end we have West Texas, New Mexico, all ones. And that's just because if we look back at the data, at the top we have Albany, at the bottom we have West Texas, New Mexico. So ones are encoded for those values that the indexes take on, and zeros for all the others. So this right here is going to be our dummies data frame. So pd.getDummies, not data, df subcolumn. And then we're going to concatenate with pd.concat two data frames together. First the original data frame, and then the dummies data frame, and on the column axis. So we're going to just paste on the dummies onto the original data frame, and then we're just going to drop the original column that the dummies were created from. Alright, and then we'll just return df when that's done. And now we have both of these ready to go. So let's take a look. If we do ordinal encoding on our data and the date column and the date ordering, which we specified above, date has become a series of numbers indicating how recent or how far into the past the example is from. So, alright, let's see. Let's do one-hot encoding. And we're going to want to encode region, right? So data region. And you can see the original region column is gone. And it's been replaced with all these dummy columns at the end. So if you notice, alright, let's actually set these. So data equals and data equals. If we look at data, everything is in numerical form except our target column. And if you remember, target column, as specified above, is type. So if we take a look at it, it just has two values, as we saw in the uniques above, conventional and organic. And we can use a sklearn's label encoder to conveniently encode this. Equals label encoder. And we can just say this equals label encoder dot fit transform data sub target column. Alright, now if we look at x.dtypes, oh, we can just do x.info, not x, sorry, data.info. Everything is an integer or a float or an unsigned int. So, it's really good. We are done pre-processing our data. We are ready to start splitting and scaling the data. So let's split. Y will be data sub target column, and X will be data dot drop target column. Alright, and then we're going to create a scalar object, which is going to be the standard scalar that we imported. And X will be scalar dot fit transform X. So now our Y looks like this, our X looks like this, scaled to have mean 0 and variance 1. And Y is going to, let's just get the shape of both of them. So Y.shape, X.shape. Alright, and so we have 65 features in the end, and 18,000 training examples. So let's split it into xtrain, ytrain, xtrain, xtest, ytrain, ytest. The train test split function. xy will specify a train size of 70%. And now we can start training. So we'll build a model, which will be TensorFlow Keras neural network. So inputs equals tf.keras.input. That takes in how many features we had? Right here, 65. 65 features. And then our next layer, our first hidden layer, will be tf.keras.layers.dense. We'll give it 64 activations and an activation function of ReLU. And let's get one more in there. And here we'll pass in inputs, and here we'll pass in x. And for our outputs layer, we'll just have one more dense layer, except here is the number of output values we'll be predicting, which is just one, which will be the probability estimate for the positive example. And the activation function here will be sigmoid to return a probability estimate, and we'll pass in x. Then our model is just going to be tf.keras.model, and we've already specified the inputs, and now we also specified the outputs. Okay, then we're going to compile our model. So optimizer is going to be atom, loss function will be mean squared error, and metrics we'll just use accuracy. Since actually it's a 50-50 split. If you look back here, I'm pretty sure, did it say? Oh wait, no, that's the wrong one. Where is it? Type. 50-50. So we don't have to worry about skewed classes. Accuracy will be a fine metric to use. Another way of checking that is if we just y.sum over the length of y will give us 50%. That's just saying this is the sum of all positive examples, or the total count of positive examples over the total count of all examples. So now we can fit our model, and let's store it in a history object. We have xtrain, ytrain, which is what we're fitting the model on. We'll give it a validation split of 20%. Batch size, let's make it 64. Number of epochs, let's make it 100. And I'm going to specify a callback function here, which will be tf.keras.callbacks dot reduce learning rate on plateau. And this callback function will run during training. That will help us converge. When it sees that our loss is not decreasing so much, it's going to reduce the learning rate so that we can get closer to the global minimum. Alright, and while that trains, you know what, actually let me make it verbose false, just so we can keep the notebook clean. Okay, why not verbose 2? Make it a little nice. Wait, what? That didn't do what I thought it would. Alright, let's check the results. While that trains, it shouldn't take too long. We're going to make a new figure. Fig size of 14 by 10. This is the usual one I make, which will just be a plot of the training and validation loss over the number of epochs. So on the x-axis, we'll have an epochs range, which will just be a range from 1 to the number of epochs plus 1. And on the y, we will have train loss, which will be the history object we created. Also has a history attribute, and we'll index that at loss. If you don't know, history.history looks like this, where it's basically a dictionary that maps the metric to the metric values across epochs. So it has one for loss and one for validation loss. So we're going to do that. Here it will be val loss, and this will also be val loss. So these are our y-axes for the two different graphs, and this will be our x-axis for both of them. So now plt.plot epochs range on the x and train loss on the y, and the label will just be training loss. And then for this, very similar, but this will just be validation loss and val loss. And we'll give it a title, training and validation loss. We'll give it the x label will be epoch, the y label will be loss, and we'll just enable the legend. Alright, let's take a look. Epochs is not defined. Yes, that's because, okay, let's do this. Okay, I'm just going to put, usually I do this so we can reference it later. Okay. I just realized I'd have to train it again if I wanted to run that block. So let's do that. Okay. And you can see it has converged very nicely, mainly due to this callback function. I ran this before. Without the callback function, it starts jumping all over the place, but with it, it starts converging very nicely down there. So let's take a look at what is the epoch with the lowest validation loss. And epoch 72, I think, has to be +1 because we validation loss goes from 0. So epoch 73 has the lowest validation loss of anything. So why not just retrain this so we can get the absolute best performance? Make this about 73. That will train. It looks like, you know, there's very little overfitting going on, but there might be just a tiny bit. So just to get the absolute best out of this model, we'll train it for the number of epochs that had the lowest validation. And it's done. Let's take another look. Should just converge as it did before. And yeah, that's pretty good. It's very close. So now we're just going to check out how it did. Model.evaluate on the test set now. And we get an accuracy of 0.9998. So that's basically 100% accuracy. That's really good. Very good. I'm amazed, actually, but with the data set we're given, that we're able to classify so accurately. There must be a tremendous difference between organic avocados and conventional ones. So that will sum up today's video. Thank you so much for watching. If you enjoyed, make sure to subscribe and hit the bell. Leave a comment you have with any suggestions in the section below. I'll see you guys tomorrow. Have a great day.